So we think we have a definition of linear dependence and independence that captures this idea we have of the spanning set for a span not having any redundancies, right? What we're hoping to capture is that a vector is linearly independent of others if the span of all of these vectors together, v together with v1 through vk, doesn't have any redundancies. So let's look at one more example to see if this definition really captures that idea. Let's check, is this vector, 1, 1, 0, linearly dependent on 1, 2, 1 and minus 2, minus 4, minus 2. So, right, at this point we know how to check this. We can put these two vectors, v1 and v2, in a matrix, augment with the vector that we want to check the dependence of, and then row reduce and see if there are any solutions, right? And again, really what we're doing here is seeing if there are any solutions to the system v equals a1 v1 plus a2 v2, right? That's really what we're doing when we're row reducing this matrix. All right, so fortunately this one is easy to reduce, so just row 2 minus 2 times row 1, and row 3 minus row 1. So 1 minus 2, 1, and then 0, 0, I lost track what I was doing for a second, minus 1. And then, in fact, we can stop right here, right? This row showing up in an augmented matrix for a non-homogeneous linear system means that there won't be any solutions. So it doesn't even matter what this last row turns into, right? This is representing an inconsistent equation. So there are no solutions to this. So that means V is linearly independent of v1 and v2. All right. So, if our definition for linear dependence really captures what we wanted to express about redundancies, then since v is linearly independent of v1 and v2, that should mean that this spanning set doesn't have any redundancies. But in fact, it does. So it turns out that if we throw away this vector, these two span the same subspace as all three together. So there was a redundancy, we just missed it, right? So this one isn't redundant, but that one was. So one problem with this way that we've defined linear dependence is that it sort of it makes one vector look special, right? So when we ask to the question up here, is v linearly dependent on v1 and v2, v is playing a special role, but this question of redundancies, there isn't any special vector. It's really all of them together that determine if there are any redundancies. So maybe what we should do is take this equation that we were trying to solve and rephrase it in a way that doesn't have any special distinguished vector. So here's the equation that we solved to decide if v1 was linearly dependent on v1 and v2. Well, we could make this look more symmetric. In other words, make all of the v's come into the equation in the same way just by moving v to the other side. So that would look like this. 0 equals a1 v1 plus a2 v2 plus minus 1 times v, right? So instead of asking about solutions to this first equation, we could ask about solutions to the second equation. But there's a clear way to make each v sort of appear in this equation in the same way, and that is, rather than saying that this coefficient is minus 1, let's just say maybe it's a3. Right. So instead of asking about if there are any solutions to this equation where v is playing a special role, maybe what we could do is ask, are there any solutions to this equation. 0 equals a1 v1 plus a2 v2 plus a3 v. Of course, right, v isn't special anymore, so maybe instead of v, we should just call it v3, just so everything looks the same. All right, note that on the left-hand side of this equation, this 0 is actually the vector 0, right? It's not a scalar 0. All right, well, you know, this equation definitely has a solution. One solution is just with all of these coefficients being equal to 0, right? This is called the trivial solution, right? By moving v to the right-hand side, we've made this a homogeneous equation, and homogeneous equations always have a solution just by choosing 0 for all of the variables. Really, what we want to know is there any other solution besides the trivial one? So what we really want to ask here, we need to insert something into this question. Instead of asking, are there any solutions to this equation, what we really want to know is, are there any non-trivial solutions to this equation? In other words, solutions where at least one of the a's isn't 0. So the question is how does the answer to that question correspond to our previous idea of linear dependence, where one vector is playing a special role? Well, suppose that one of these a's isn't 0, so maybe it's the first one, right? If one of these a's isn't 0, so if we have a non-trivial solution, that means that we could move that vector to the other side, like this, and then because a1 isn't 0, we can divide everything by a1. So then we get v1 is minus a2 over a1 v2 plus negative a3 over a1 v3. And we sort of reproduce our previous definition of linear dependence, right? So the upshot of this is asking this question, are there any non-trivial solutions to this equation? The answer to this question checks for whether every vector is linearly dependent on all of the other vectors. But it answers this question sort of all at once, rather than having to check each flavor of linear dependence individually, right? We don't have to check, is v1 dependent on the v2 and v3, and then is v2 dependent on v1 and v3, and then is v3 dependent on v1 and v2. Rather than answering those three questions separately, we can just ask about non-trivial solutions to this equation and get an answer sort of all at once. So that's what we'll do. We'll discard our old definition of linear dependence and replace it with this. So if we have a collection of distinct, that is to say different vectors, v1 through vk, we'll say that this collection is linearly dependent if the only linearly dependent if this equation has a non-trivial solution. A non-trivial solution is called a dependence relation or dependence relationship. If all of these vectors, if the only solution to this equation is the trivial solution, then we will say that this collection of vectors is linearly independent. And so remember, linearly independent, what that should mean is no redundancies when we take a span, right? Okay, so let's check to see how this definition works. So is this collection of vectors linearly dependent or independent? Okay, if it is linearly dependent, that means we should be able to write one of these vectors as a linear combination of the others. All right, So remember what so let's name this v1, v2, and v3, just so I don't have to write out the vectors all the time. What we need to know about is solutions to this equation. a1 v1 plus a2 v2 plus a3 v3 equals 0, right? Vector 0. So we need to know, are there any solutions to this equation? Well, we can just check. This is a homogeneous system of equations, so let's solve it like it's a homogeneous system of equations. Minus 3, 0, 4, 8, minus 1, 7, 2, minus 1, 1. Actually, I think what I'm going to do is, right, the order of the vectors is arbitrary, so just to make the row reduction a little easier, I think I'm going to put this vector first. So 2, minus 1, 1, and then I don't know which one is going to be better, so let's do this one. And then 8, minus 1, 7. Okay, so I guess I've changed the order, so I've put this one first, so that's v1, and this one second, so that's v2, and then this one third. Okay, now since we're solving a homogeneous system, we don't need to augment this to keep track of the right-hand side, because the right-hand side is 0. So, all right, now let's row reduce. So let's see, maybe the easiest thing to do would be just to switch row 3 and row 1. So 1, 4, 7, 2, minus 1, 0, minus 1, and 2, minus 3, 8. And then let's add row 2 and row 1. And let's take row 3 and subtract twice row 1. So 1, 4, 7, 0, 4, 6, and then 0. So this minus twice that is minus 11, and this minus twice that, so 8 minus 14 minus 6. Okay. All right, now we can do, I guess, row 2. Let's divide row 2 by 4. So that's going to give us 1, 4, 7, 0, 4, 6. Sorry. Divide this row by 4, so that gives us a 1 and 3 halves. There we go. And then 0. While we're at it, let's stick a minus sign on row 3. So that flips these to pluses, so 11 and 6. All right, and now we'll do row 3 minus 11 times row 2. All right, so 1, 4, 7, 0, 1, 3 halves, and then 0, 0, and then, let's see, 11 halves minus 33 halves. I better write this down. Minus 33 halves plus 6 is 12 halves, so minus 21 halves, right? Yeah. Okay. All right. So at this point we can stop, because remember what we're trying to figure out is, does this system have any non-trivial solutions? And we can see there's a pivot in every column. Right? So when there's a pivot in every column for a homogeneous system, that means every variable has to be 0. But that's the trivial solution. So because there's a pivot in every column, we only have the trivial solution to this equation up here. So what does that tell us about dependence or independence? Well, if the only solution to this is the trivial solution, that means that these 3 vectors, v1, v2, and v3, are linearly independent. All right, so these are linearly independent. All right, one more example. Let's check this one. are these vectors linearly dependent or independent? And again, if they are dependent, we should be able to write one of them as a linear combination of the others. Same idea here. I think I think it'll be easier to put this one first, and then this one, and then that one. So -2, 1, 3, 4, 2, -5, 26, -26. Okay, now we're going to do row reduction. And actually, I'm going to do this off screen so you don't have to watch me do row reduction again. All right, we're back. Here's the reduced row echelon form. Anytime I leave off an entry, it's 0, so I guess I'll write them all in. Right, okay. So, as you can see, there is a free variable. So, right, this column is representing A1 in the system. This is representing A2. This is representing A3. There is a free variable, so that means there are non-trivial solutions. So free variable here means non-trivial solutions. Okay, and since we have non-trivial solutions, that means these three vectors are linearly dependent. Okay, that means that one of them is redundant. The question is, which one is redundant? Now, as we've seen, if we can write a linear dependence relationship, any vector that has a non-zero coefficient, we can treat as the redundant one. To do that, we just need to actually find values for these coefficients. So if we write out the solution set to this system, we get A1, A2, A3 has to be, so A1 has to be 2 times A3, A2 has to be -4 times A3, and then A3 is free. Now remember, we just need a solution, right? It doesn't have to be any particular solution. For a linear dependence relationship, we just need some solutions. So I'm just going to kind of arbitrarily choose the nicest one it looks like we have. And in this example, the nicest one is going to be 1. If we had some messy fractions, we might cook up a solution. We might choose a free variable to make all of the fractions turn into integers once we work it out. But in this example, we don't need to worry about that. So when A3 is 1, we get the particular solution 2 - 4, 1. So that means that the 0 vector is 2 times v1 minus 4 times v2 plus 1 times v3. Okay. Now remember, we can choose any one of the any vector that has a non-zero coefficient and use it to write that vector as a linear combination of the others. So here we really have a choice because every vector has a non-zero coefficient, right? So here's our linear dependence relationship. So let's see, we could write v1 as a linear combination of v1 and v2. Just move the v1 term to the other side. So -2v1 equals -4v2 plus v3. And then, right, finish solving. So divide both sides by -2. So v1 is 2v2 minus 1/2 v3. And this displays v1 as a linear combination of v1 and v2. Of course, we could do that with v2 or with v3, you can do v2, but it works for any vector that has a non-zero coefficient. If we moved v3 over, then we'd have minus v3 is 2v1 minus 4v2, and then multiply by -1, we get v3 is minus 2v1 plus 4v2. All right, so if we want, we can display v3 as a linear combination of v1 and v2. And if you want to, you can figure out v2 as a linear combination of v1 and v3. All right, so what we're seeing is that this definition of linear dependence and independence that we've made, this is, we think anyway, this is capturing the idea of no redundancies, right? If one of the vectors is a linear combination of the others, this will detect that. And not only will it detect that, we have this way of actually calculating if a collection of vectors is linearly dependent or independent.